Hello everyone. I just made the coolest gadget of the year. It's a software-defined radio based on the MOS technology 6502 CPU, which is celebrating its 50-year anniversary on the 8th of September, or thereabout, depending on who you ask. If you know what a software-defined radio and a 6502 is, then yes, you heard that right, a 6502 SDR. And if you have no idea what an SDR is, here's a quick recap. Software-defined radios, or SDRs, are the Swiss Army knives of radio frequencies. Instead of making purpose-built hardware for the specific use case, like a garage door opener or a satellite receiver, you hand off the complexity to software, and instead of having a shack full of electronics, you plug a device into your computer and let it do the filtering and demodulation. And if anything changes, it's just a matter of changing a few bits and bytes instead of coils and caps. That means you can decode airplane transponders, listen to shortwave radio, get data from satellites, and basically anything you can imagine, with just a single device. SDRs come in a variety of sizes. Some are just USB sticks with antenna connectors, some have FPGAs and tons of processing power on board, some are self-contained units with screens and upgradable software, and some just look like walkie-talkies. I got most of these years ago, but I've linked to their modern equivalents in the description. They come at a lot of different price points too, from about $30 to thousands of dollars. Some only receive and some are capable of transmitting too, and generally vary on frequency range and simultaneous bandwidth. And in my case, it looks like this. An Arduino-style shield I intend to use with the smallest of my 6502-based computers, the 6501. If you also want a recap of what a 6502 is, it's the CPU that powered the Apple I and II, the Commodore computers, Nintendo Entertainment System, Ataris, and a million other things. And this year, it's 50 years old. In very simple terms, all an SDR does is focus on converting the incoming analog radio signal into digital streams a computer or a powerful microcontroller can handle. Essentially, what SDRs have in common is they consist of an RF frontend, mixing to IQ baseband, and digitizing the two channels using an ADC. First, the RF frontend is typically some basic band filtering and amplification of the incoming signal from the antenna. From there, the incoming signal is either directly sampled by a fast ADC or down-converted to baseband by mixing it with a local oscillator running around the frequency of interest, the in-phase signal. We also use the same local oscillator with a 90-degree phase shift to generate the quadrature phase signal. The result is we get the band of interest and a copy of the band with a 90-degree phase shift. This is the point where most people think of it and then ask, why? What's the point of the exact same signal twice but at different phases? It comes down to the inherent problem of sampling a signal. When sampling using an analog to digital converter, we only get a series of snapshots, so we lose some of the information. This causes mirroring and aliasing of the signal. The mirroring, or Hermitian symmetry, you can intuitively think of as waves passing over the ocean. If we only take snapshots and try to guess how fast it's going, we can still measure that, because we can see the slopes of the waves. But if we only have a single frame locked in time, we can't see if the wave is moving one way or the other. So if we try to graph the signal, we'll have to plot both the positive and negative wave speeds, or frequencies. Aliasing, and that it can seem to cause negative frequencies, is also intuitively hard to grasp. Even if I see the math and I have to agree it's correct, it still isn't easy to make it all sit right. Aliasing is just an artifact of how we sample our signal, making frequencies fold over each other, appearing negative. The example that clears it up for me is the wagon wheel effect. If we look at a spinning wheel on camera, going faster and faster, eventually we'll see the camera refresh rate can't keep up, making the rotation look slower, distorted, and even appear to be moving backwards, when in reality we know the wheel is always moving forward. This phenomenon is explained by the Shannon-Nyquist theorem, which states that to perfectly reconstruct a continuous time signal, the sampling rate must be at least twice the highest frequency present. If not, higher frequencies alias or fold back into the Nyquist band, appearing as negative frequencies, or at least where they shouldn't. In the software GNURadio Companion, which comes with GNURadio, this is easy to demonstrate in both the time and frequency domains by taking a look at what happens when we sample a generated complex signal. A bit more on what makes it complex later, of a higher and higher frequency until it exceeds the Nyquist limit. Since this is set up as if we had a good old sound card sampling at 44.1 kHz, we see the time domain signal gets more and more distorted the more we increase the frequency of our virtual signal source. And when we pass half the sampling rate at just over 22 kHz, our peak moves to the negative side. Of course, it still doesn't make intuitive sense to say the signal is oscillating at minus 10 kHz, but if we remember that the original signal we're mixing down to 0 Hz, or baseband, is usually far away from 0 Hz, it's also pretty easy to imagine minus 10 kHz as whatever is going on 10 kHz below the center frequency. What I'm saying is, don't get bogged down by the whole idea of negative frequencies. Just treat it as the distance to the center frequency, or the error you get when you don't sample fast enough. This video hasn't even gotten to the fun stuff yet, and I could spend hours talking about the math behind all of this if I had to. Don't worry, I won't. But if you're really interested to know more and you like to see the math presented with amazing animations and an easy to follow teaching style, I suggest you check out Marshall Bruner's videos on both aliasing and IQ sampling that I've linked in the description. The takeaway for now is that we need both an I and a Q channel. Said another way, a complex signal composed of a real and an imaginary component, to mathematically separate the signals from their mirrors, in practice, doubling the usable bandwidth. We'll get back to GNURadio a bit later, but because I really want to talk about the circuits that turn this little thing into an SDR powered by a 6502, let's move on. But first, I have to spill the beans on how I can afford to keep making projects like this. It's all thanks to JLC PCB. JLC PCB offers affordable, reliable, and accessible PCB fabrication and assembly services, making it simple for electronics enthusiasts like me to turn ideas into working boards. And I'm not just saying that because they sponsor me. I was a customer long before our collaboration began. Their platform is straightforward to use, and over the years they've been extremely supportive. Even when I pushed the limits of their design rules, working with them has honestly been a valuable learning journey. If you haven't tried JLC PCB yet, you can get your first PCB for only $2 and claim $70 in coupons. Returning users also get a fantastic offer, $30 off advanced 6-layer PCBs with features like VIN-Pad for just $5. They've always delivered, easy to work with, cost-effective, and dependable every time. Thanks to JLC PCB, I get to enjoy making new projects and share the extra boards until they're gone. So with that out of the way, what exactly is it I've made here? As I've used some gold-plated copper text to show here, the PhaseLoom is a Quadrature Sampling Detector phase-locked loop LO synthesizer SDR frontend. It's a prototype, so at this point we can't even be sure it works, let alone what performance we can get out of it. As we saw before, the basics of what we need for an SDR is an RF frontend, a local oscillator, mixers for both channels, and some way to digitize the IQ baseband signal. The RF frontend doesn't do much at this point, as it's just a 150 MHz low-pass filter. Way too wide to be practical, but I'll get to that later. The most interesting part about the circuit is the Quadrature Sampling Detector, which is based on the principle that you can make an RF mixer from switching the incoming signal on and off at the frequency we're interested in and store the sample in a capacitor. For that, I'm using a pretty fast 74C BTLV 3253 analog multiplexer. The principle of switching mixers, or commutating mixers as they're called, has been around since the 50s or 60s, but for our purpose here it was popularized by Dan Tayloe around the turn of the millennium. Very simply put, it generates the in-phase and quadrature signals by chopping up the waveform and storing each phase in the output capacitor. Since we're only interested in the 0 and 90 degree signals, we could just use those and be done with it. But since the other outputs at 180 and 270 degrees have the complementary signal, we can use those to get bigger amplitude and better noise immunity by treating them as differential signals. Said another way, instead of having just a single wave referenced to ground, we use two inverted waves and essentially get double the signal out. As you might notice, I used this trick twice since I have a transformer on the incoming RF that turns it into a differential signal, so the second switch set of the 743253 contains the 180-degree signal compared to the first one, again improving the signal level and noise immunity. Great! The Tayloe-style detector usually needs a switching speed of 4 times the operating frequency. And since I'm using the very popular SI5351 clock generator that has a maximum frequency of less than 200 MHz and a decreasing resolution the higher it goes, I thought that's going to be a severe limitation to the maximum frequency. But luckily, I'm not the first to try a design like this, and I saw NA5Y on YouTube got around this limitation by using the phase offset feature of the SI5351 to use 2 channels to generate a 0 to 3 gray code count by having the same frequency 90 degrees out of phase, which means the count changes 4 times each cycle, even though the frequency itself is only 1x. That does come with a downside, as we'll see later, but it might just be worth it anyway. Since this is a prototype development board, I've broken out the 3 channels of the SI5351, so even if this whole thing doesn't work, we can still use the clock generator for other things. But let's see if it works. Over the summer holiday, I've been playing a bit with the super cheap SI5351 modules, so I know my 6502 assembly code works, but I guess it's time to see if it also works on my design. The 65 Arduino underneath the shield is usually meant to be used with an SSD 1306 style OLED screen, but I have very intentionally left it out for the PhaseLoom because it generates a mean amount of noise. Not only when the I2C lines switch, but also because the screen's internal refresh is pretty noisy. And we don't want that near our RF or our audio. But that doesn't mean we can't use the 65 Arduino's built-in I2C scanner to see if the SI5351 responds. And it does. We can see the display itself shows up at address 3C, an I2C EEPROM on the 65 Arduino at 50, and the SI5351 at address 60. Perfect. I guess technically we can just connect an antenna and a speaker and we should be able to hear something. Even though we're supposed to be sampling the INQ signals with an ADC and not with a speaker, there's nothing preventing us from listening to the signal coming out of either channel, except for the fact that the signal will be very low. For that reason, I've cheated a little bit ahead of time and put a little NS8002 speaker driver IC on a little breakout board with a little 8-ohm speaker so we can listen straight to the outputs. It's one of those little ICs you'll typically find in a portable Bluetooth speaker. Since both channels are the same signal 90 degrees out of phase, we won't even be able to hear the difference between the I and the Q channel, so it doesn't matter which one we hook it up to. I've also cheated a little bit ahead of time and written a bit of code to control the SI5351 from the 6502, which is already available on GitHub, of course. So the PhaseLoom is already outputting what I hope is right around 7 MHz, and we can change the channel using the buttons. As we can hear though, with this antenna and this time of day, not much is going on at 7 MHz. But technically what we have here is already an HF receiver for the 40 meter band. Technically. Very technically. Is it an SDR at this point? Not really. Also, we can't be sure we're actually listening to 7 MHz, so we need a known reference of some kind, and I don't have an HF transmitter lying around. But I do have my bigger 6502 single board computer with some clock divider lines, and since I can throw a wire on an 8 MHz output, we should be able to hear the noise from that. If I switch the PhaseLoom to 8 MHz, we can already hear the increase in noise. Since I bet there's lots of 8 MHz noise around my office, including from the 65 Arduino the shield is mounted on. But if I power on the computer, we should hear the difference. And wow, that's loud and high-pitched. The reason we can hear it at all is the SI5351 with the 25 MHz crystal isn't perfectly calibrated, and neither is the 16 MHz crystal, the 8 MHz signal we're listening to. So what we hear is actually the difference between the 8 MHz clock of one computer and the best try the SI5351 can make without calibration. In a perfect world, we wouldn't hear anything at all, since 8 MHz minus 8 MHz equals 0 Hz. But clearly that's not the case here. And if I go so far as to touch the crystal legs with my fingers, we can even hear I can detune the crystal with the capacitance of my body. So we've confirmed we have an HF radio we can tune. That's pretty cool and certainly worth building this board for, but we can do even better, because we want this to be a real SDR. So the next step is taking our I and Q channel and digitizing them by sampling them with an ADC. Ideally, I'm hoping for several megahertz worth of bandwidth, but before we get there, I'd like to take a pit stop at the time when software-defined radios were super expensive and not super capable. When Dan Tayloe was working on his white paper around the year 2000, when the 6502 was half the age it is now, SDRs were mostly a military technology, and ADCs you could hook up to your computer were super specialized and probably called data acquisition cards, priced around $1,000. But there was another kind of ADC most people already had built into their PC, the sound card. Around the year 2000, a sound card was already basically integrated into a single IC, doing digital to analog conversion and amplification to get sound out, and analog to digital conversion to get sound in through the microphone and line in inputs. For the past quarter of a century, though, getting two channels synchronized into the computer has drifted towards something you do with a USB sound card, since most internal ones in both desktops and laptops only have a single input channel. To test it out, I've made a little SMA to mono quarter jack cable so we can get our baseband IQ into GNURadio. I've made a little project that'll show the two channels and also convert them to a complex signal we can use to make an FFT, waterfall, and combined IQ. To successfully remove the mirror, we need the I and Q channels to be balanced perfectly, and any mismatch will show up as a lack of image rejection. With the PhaseLoom tuned to 7 MHz and our noise maker turned off, we basically see silence, which is a good thing. If we turn on the other 6502 computer and tune to 8 MHz with the buttons, we get this. A complete mess of aliases and images, and yes, we do see our 8 MHz signal, but we also see so much junk on the spectrum we're not interested in. First of all, the signal we're looking for is a noisy digital 8 MHz square wave which produces all kinds of harmonics. And second, I've designed the PhaseLoom to output a much wider bandwidth than the 44.1 kHz the sound card is sampling at. And like we skimmed over before, we know from the Shannon-Nyquist theorem that means everything outside our frequency range folds back as aliases, which explains why we see so many peaks. But something else isn't quite right either, because both sides of the spectrum look completely identical. And since both I and Q looked like they have about the same amplitude, we should be seeing at least some image suppression. I think it's going to be hard to figure out what's going on without bringing out the oscilloscope. But even then, that noisy square wave might be a problem. I've always been a bit cheap when it comes to equipment. So when I really needed a scope a few years ago, it was either a low performance, old used analog scope or something off the beaten path. Luckily, around the same time, the FNIRSI 1013D tablet scope had just come out. And I'm super happy I bought it because it's much closer to a real scope than some of the other budget scopes, and in terms of bandwidth and sampling rate, it's much better than a used old analog scope. If you're looking for a budget battery-powered scope, I'd absolutely recommend it. But the reason I bring it up is that the 100 MHz bandwidth isn't quite enough to scope the frequency range we're hoping to get out of the PhaseLoom. So why do I even mention it? Well, as a total coincidence, as I was planning this video, FNIRSI reached out to me and asked if I wanted to try some of their products. I explained the situation and they sent me this for free. It's FNIRS's new DPOS350P, 350 MHz 1 gigasample tablet oscilloscope, and it's exactly the performance upgrade I need for this project. The reason I'm super excited about this, first of all, is that if I went out and wanted to get a new 350 MHz scope from some of the big brand names, we're solidly into the thousands of dollars range. And this one is for sale for less than $300. And I got it for free. And second, it comes with a built-in signal generator that can make a sine wave up to 50 MHz, which is exactly what we need to test the PhaseLoom. It comes with decent-looking probes, power supply, manual, and a practical case. I don't do reviews on this channel, and of course I can't do an apples-to-apples comparison of this and a big brand 350 MHz scope, but if a company that makes products I need for a video offers to help out, I can't imagine refusing for principles. I got the scope for free, but FNIRS didn't ask for anything in return and completely respected my creative freedom. Oh, and that's a surprise to me. It looks like it even has a spectrum analyzer built in. That'll come in handy at some point. The scope is pretty intuitive, and I don't think I'll be needing the manual for what we're doing today. So, where were we? Yes, with the new scope, we can kill two birds with one stone, as we don't have to rely on the noisy 8 MHz square wave, but can just set the signal generator on the DPOS350P to output a 7 MHz sine wave. Since that band was more silent, we'll get a better representation of the signals because of the increased scope bandwidth. Yay! So with GNURadio Companion ready, we just set the scope to output a 7001 kHz sine wave, and we should see a single peak on the FFT. But unfortunately, we still see two peaks, which kind of tells us something is wrong with our IQ signals. To get the image rejection we want, we should see the 7 MHz signal on both channels 90 degrees, or a quarter, apart. Let's take a closer look at the signals. If I zoom in on the waveform, we unfortunately see both I and Q are completely in phase, which is absolutely not what we want. So the good news is that we're successfully mixing down the 7 MHz signal down to baseband, and we see our 7001 kHz signal at about 2.4 kHz, which means the SI5351 is at least 1400 Hz off. But that could also be the image further away. And this is why we need a well-balanced complex IQ signal to begin with. Since it looks like it's mixing reasonably, let's take a look at the signals we're clocking the mux with. Since if the count isn't right, the quadrature won't come out right. This is when it comes in handy I broke out all three channels of the SI5351. I don't have a good pair of probes to attach to the SMAs, but I think a pair of resistor leads will do just fine to check if the signal comes out in quadrature. So it's not the prettiest 7 MHz signal I've ever seen, but the 90-degree phase offset seems pretty spot on. I wonder what else could be the problem. Unfortunately, it turns out I messed up the count after all, and the old version I managed to send off to production wasn't wired for the gray code count of 0, 1, 3, 2, but the normal binary 0, 1, 2, 3 count, meaning the 270 and 180 degree phases were swapped around, resulting in identically looking phases for the I and Q outputs. Whoops. Luckily, I had little enough confidence I'd get everything right the first time that I added 0 ohm resistors between the sampling capacitors and the op-amps, which comes in handy now as I don't have to cut traces, but can just remove the two resistors and add jumper wires to swap I and Q to correct my mistake. Now that we're sampling the right phases, we'll hopefully see something more reasonable when we open up GNURadio Companion. And if we turn on the signal generator at 7.001 megahertz, we only see a single peak, which is exactly what we want. To be honest, I'm actually surprised we don't see the mirror at all, and it's well below the noise floor, even though I just roughly adjusted the volume controls to make each channel have about the same level for I and Q. I'll take any win I can get, because now we're almost ready to try this software-defined radio as a radio. Why do I say almost? Well, first of all, we're missing an antenna for some sort of band we can actually listen to. And we can technically tune to anything between 8 kHz and to over 160 MHz. But the thing is that since a quadrature sampling detector works on the principle of sampling the incoming signal phases at the local oscillator frequency, we run into aliasing not only when sampling with the sound card or ADC, but we will also be folding down aliases of each band that's a multiple of the LO frequency. Let's imagine there's a strong FM radio station at 91 MHz. That's exactly 13 times an LO frequency of 7 MHz, which means we will get some of that signal mixed down to the band we're listening for. That makes bandpass filtering so much more important, so we're going to need a filter of some sort. Antennas and filters are a whole field of science by themselves, and I'm not going to go into the math. You can find a bunch of online calculators that'll help you out if you need to get the math for specific ones. But since I knew I was going to need a few different ones, I've had a bunch of these somewhat universal filter PCBs made. The idea is you can use either SMD, through-hole, or wound inductors together with the usually smaller capacitors. Most combinations of basic 5-element filters are supported, so it's easy to make a low, high, or bandpass filter. And since it's cutting up the frequency bands, I had to call it the PhaseBlade. Since I have a 7 MHz antenna or 40 meter band antenna in hamspeak hanging in my attic, or maybe antenna isn't the right word. I have two pieces of somewhat tuned wire hanging under my roof that goes to my garage through an antenna cable. That's more accurate. Since we're aiming for 7 MHz, I made this bandpass filter that should keep the higher bands from aliasing in. I didn't have any reasonable inductor cores at hand, so I had to make air cores held together with Kapton tape. It's not pretty, but it should work fine too. If we put that between the PhaseLoom and the antenna, we should see a difference. It's not much, but I think we can see the noise floor dropped a few dB and looks a bit cleaner. We didn't see the image frequency before, but now it's actually visible. It could be because the noise floor dropped enough for us to see it, but it could also just be because the probe the signal generator is hooked up to is closer to the antenna. But the preselector filter seems to do its job. When I explained aliasing in the beginning of the video, I used a generated signal source to demonstrate it. But now we actually have a setup where we should be able to demonstrate it with a real, complex signal. So if I take the 7 MHz signal coming out of the signal generator and mix down to baseband and keep increasing it until it goes over the Nyquist limit at 22,050 Hz, we should see it go over the right edge and show up on the left. The funny thing, though, is that when I increase it a tiny bit more, we see it's attenuated by quite a lot. Actually, we almost can't see it when it's just 1,000 Hz above the alias we could clearly see before. Why is that? Well, we're using a sound card as an ADC here. And of course it isn't made to sample anything above 48 kHz, since the aliasing would be audible as well. Wouldn't be very professional if your sound card started picking up weather satellites. So it has a low-pass filter with pretty sharp skirts built in, meant for audio frequencies. If I keep increasing the frequency, we might see some places the filter has some ripple showing up as noise in the passband, but it doesn't look like we see much. What does this mean for us? It might mean I made these two low-pass filters for no reason, since the sound card already have them built in. But let's give it a try anyway. The funny thing is, the sound card just sees silence when the signal starts aliasing, and by the look of it, the sound card also turns off some internal amplification, making the noise floor drop even further. We might not need the filter, but again, it does seem to decrease noise a tiny bit as well. I think it's time we try this connected to an actual antenna, so let's move this show to the garage. I've tuned the PhaseLoom to 7.07 MHz, which means the small signals we see on the waterfall are FT8 digital mode signals. We could probably decode them if we wanted to, but let's come back when the night shows and signals grow on radios. I'm now a bit closer to sunset and I've tuned it to the beginning of the 7 MHz band, and as we can see, there's a bit of CW traffic going on. For the uninitiated, CW stands for continuous wave and counterintuitively means Morse code, because it's a continuous sine wave that's switched on and off, as opposed to early spark gap transmitters. I don't think I've ever noticed how high the noise floor is on this antenna before. There's no RF amplification at all, and the only amplification going on is the mixer itself and the op-amp after the mixer. When looking at the scope graph, it's easy to see there's quite a lot of noise energy coming into the antenna, and my guess is that's just the cost of having the antenna above and around basically all my house electronics. So, is this a 6502 based software-defined radio? Yes, absolutely. Most other SDR dongles require a bigger computer to do the DSP anyway, so it's certainly within the definition, even though the 50-year-old CPU doesn't do any of the DSP. The magic of an SDR, no matter the price or performance, is that we can filter, tune, and demodulate in software, and that's exactly what we're doing here. Is it done? No, absolutely not. The PhaseLoom is just a development board and the center of a platform that I'm going to expand little by little. As it is, it's a fun, amazing little gadget that'll work fine like this as a cheap narrowband HF receiver, but I think it's missing at least two important things. First of all, while listening to the lower amateur radio bands is fun, I do want this to be a useful SDR platform, so it'll need another mixer in front of it, so we can do more than just direct conversion in the RF frequency range of the SI5351, ideally up to several gigahertz. Second, we've only just scratched the surface of IQ sampling, and it's obvious we need a dual-channel ADC with way more bandwidth than a 44 kHz sound card, and we need a driver so we can change the frequency directly from GNURadio or something like GQRX. Third, I'm not done with the 6502. And I think it would be really cool to hook up a parallel ADC and actually do a little bit of digital signal processing on the 6502. Like at the very least, Goertzel's algorithm for tone detection, or maybe even a small FFT. There's a lot of work to be done, and I haven't even touched on the 6502 code. I've written a little 6502 assembly library to control the SI5351, and I've skipped the heavy math on the 6502 for now, so it uses lookup tables to set the frequencies. The source code is on GitHub together with a spreadsheet that makes it easy to create the LUTs for a new set of frequencies. Since the PhaseLoom is an Arduino-shield form factor, you don't have to use it with a 6502, but can hook it up to anything that has I2C, whether it be an Arduino, ST Nucleo board, or an ESP32. The 6501 I'm using it on here is just for fun and because it forces some well thought out assembly code and understanding of the lower levels that you usually don't get from an Uno and a ready-made library. All the schematics, hardware files, source code is freely available for you to use and modify the way you like, and I'm also selling the boards I have left over on my store, linked in the description. Since I messed up the IQ sampling order, I will fix every board I sell, just like I did in this video, since honestly, they're too costly to throw away. When they sell out, I will probably have another batch made without all the SMA connectors factory soldered. If you're the DIY type person, I've already fixed the design and have the new PCB available for those who don't mind doing a bit of SMD soldering. JLC PCB and FNIRSI deserve a big thanks for the support in making this video, as my wife certainly wouldn't let me buy all these things myself. I've put links to all the products and other content mentioned in the video in the description, and I hope you like this lower level look at making a software-defined radio platform from the ground up. Either way, thanks for watching.